So today we will be covering the third lecture on fault simulation. So what we have discussed in the last two lectures, that to find out the test patterns for stacked faults, there can be two basic approaches. In one approach, we sensitize the fault, propagate the effect, and then justify the lines, which is called the sensitization, propagation, and justification approach. Then we have found out that this actually the algorithm is not a very simple algorithm, because you can see that first you have to sensitize, then you have to propagate, and then you have to justify, and you have to repeat for all the stacked faults, and sometimes they may be requirement of iterations, because sometimes your propagation or your what you may call the justification may not be successful. So, and also there is a fact that one pattern can detect more than a number of faults. So, if you are doing sensitize, propagate, and justify for different faults, so what may happen is that you may be landing up in returning the same pattern for detecting multiple faults, which is not a problem, but the thing is that the same algorithm or the same pattern you are generating by running the sensitize, propagate, and justify approach multiple number of times, which is actually hampering your efficiency. Then we have seen that another approach, which is called the random fault simulation based test pattern generation approach, in which the idea is you take a random pattern and then you find out how many faults get detected by that approach. So, if you find that there is some k number of faults are detected by that, then you drop those k faults and then you take another random pattern and keep on doing it till you find out that a new random pattern is not able to detect some sufficiently less number of faults. So, the idea is better than the previous approach, because you can see that one pattern detecting k number of faults, so that can be found out by random fault simulation, can be found out by fault simulation in one go. So, you need not repeat sensitize, propagate, and justify for these k faults. So, but we can do this only for the easy to test faults, after which this process saturates, and then we have to obviously go back to sensitize, propagate, and justify approach. And then what we have seen, that we have seen different kind of fault simulation examples. So, what is the basic idea of fault simulation was that we have a normal circuit and we have a fault circuit, and then we find out whether a pattern creates a behavioral difference at the output with the fault. So, we have seen very simple serial fault simulation, which was the very simple one, in which case what we do, we take up fault and we take a pattern and then find out whether one fault is detectable or not, and then if it is detectable, it is drop the fault and you try with another fault and keep on doing it, then you apply another random pattern and so forth. But actually the idea here was that it was very slow, because we are going for serial based approach, one fault, one pattern, one fault, then next fault and so on till you cover all the faults, and the process repeats for the next test pattern. So, we have seen that this is actually a bit slow. Then when we have gone for parallel fault simulation, in which case for each line we have a array which represents some n bits, or which is depending on the parallelism of your computer, you can have a n bit array or a 2n bit array or something like that. One bit represents the normal circuit and the all other bits of the array represent one faulty case each, and then we can apply the random pattern, and then we can find out how many faults can be detected by the random pattern. And if your window size or your array size is n, then we can deduce the reasoning about n minus 1 fault, because one bit is for the normal circuit, that we have discussed. So, that parallelism enhances your algorithm by a factor of n minus 1 if n is your window size or your array size. Then we have seen that in this case, what is the idea, that if your computer bit processing or what you call the parallelism of the processor is low, or it is only 32 bit and also if there is some 1000 faults, so at least you have to repeat it 1000 by 32 ceiling factor, that number of times you have to repeat the what you call this parallel fault simulation. So, then we found out, then we started discussing about another algorithm, in which case can we do the whole thing in one go, that is we apply one random pattern and in one scan of the circuit can we deduce the results about all the faults that can be detected by this. Then we saw that deductive fault simulation was a very good approach for that, in which case we apply one random pattern and then at each net of your circuit, this one, this one, this one, and this one, we find out what are the fault, or we find out the fault list that it is detectable by that random pattern, and then actually you can in one go find out which are the patterns detectable by that fault. Then we started finding out some rules, like for example, if it is a NOT gate, then whatever is the fault list here, you propagate the value here, and then if the value here is a 0, then we have to also add if the value here is a 1, then you have to add a stacked 1 at this net, and if here the input signal value is 0, then you have to apply a stacked 1 fault here, and the whole list from here propagates here. Then if it is a fan out array, then whatever is here gets propagated here and here. in addition to if it is a 1 signal here, you detect a stuck at 0 and vice versa. And then similarly we have seen the rules for an AND gate, like if the case is 1 1, then whatever fault list at both the nets will be added here, plus some stuck at 0, stuck at 1 at the output. Then if it is 0 0, then we have found out that only the common set of faults in between this can propagate to the output. So we are studying out some kind of rules in deductive fault simulation, which can basically, if you scan the circuit from input to the output, you can find out what the faults can be detected, but for that we require some rules. So in the last lecture, so we covered some rules, like for example, if it is a fan out net, then whatever fault list here propagates here. So you see this list here and this list here, then you are applying a random pattern 1 over here, sorry, yeah, you are applying a random pattern of a 0 over here. So the pattern applied is a 0 over here. So it detects a stuck at 1 fault here. Similarly, it also and the value is 0 0 over here, signal value, because they are applying a 0. So a stuck at 1 is detected at this net and a stuck at 1 is detected at this net. And for the inverter, what is the rule we saw, that whatever here and whatever here, both the lists will be here. Now this value is 0 0 here, so it is 1 1 here. Okay, so some stuck at 0. Sorry. So this is the stuck at 0 that will be detected here, and this is stuck at 0 that is detected here. Now you know that for the AND gate, what we have seen the rule, for the AND gate there will be 4 rules. Okay. So for 0 0 0 1 0 1, then you have for 1 0 and then for 1 1. So for all the 4 cases of your AND gate, you have to have the rules. So in this case it is 1 1. So you know that in an AND gate, when both the inputs are 1, then if this input is 1, then whatever fault effect will propagate. Similarly, if this is 1 here, so whatever is the fault effect can be propagated, because 1 is the non-controlling input of an AND gate. But if it is 0, you know that nothing propagates the other end. So in this case, both the values are 1 1 signal values, because of the random pattern 0. So whatever the list over here and whatever the list over here, whole thing you know that it will come over here. So you can, if you study this list and this list, so the whole list will be actually taking care of this one and this one, because we are applying 1 1. And 1 1, the signal value output is 1. So you can also detect a stuck at 0 fault at this net. So this becomes your what you called the pattern. I mean, these are the fault list for this for this random pattern 0. You can detect this any number of faults. So we found out that the rule for AND gate, when both the inputs are 1, then all the faults at both the inputs of the input and stuck at 0 at the output of the AND gate. This is the rule for AND gate when everything is 1. Then we have taken the case when the output here was a 1. So you can detect stuck at 0 fault over here, stuck at 0 fault at this net, okay, and then this will be 1 over here. So you get a 0 over here. So the whole list comes here because of this inverter, and then you can add a stuck at 1 fault at this net, you can add a stuck at 1 fault at this net. Now we have also discussed in the last class that at both the AND gate inputs are 0, then if the AND gate input is 0, one input is 0 in AND gate, we know that the fault cannot be propagated by the other end. So what did we found out, that only one fault which is common to both of them. So this fault is common to both of them. So this is landing up in a stuck at 0 over here and stuck at 0 over here. So that is the only fault which can be detected at the output, that we have seen, that only fault which is common to both of them, it can be detected over here, and of course you get a 0 and a 0 over here. So a stuck at 1 fault at this net can be detected. So both this this is the fault common, that is stuck at 0 fault at this line, is affecting both this input and this input. So this is common. So that is the only thing will propagate here, and other things will not be propagated. So the rule is, when both the inputs are 0, then we thought that intuitively nothing could be propagated, because if any one gate of the input is 0, then nothing propagates to the AND gate. But we were surprised to find out that in this case, if some input is there which is affecting both the inputs of your AND gate, then that is the only fault that is propagated. So fault list of the AND gate comprise, when both of the AND gate inputs are 0, all faults which are common to both the inputs. So only this fault was common to both the inputs, and that get propagates, plus a stuck at 1 fault at the output is obviously detected, because 0 and a 0 here leads to a 0 over here. So these rules we have seen in the last class. Now there are two more rules which remain, that is for an AND gate, that is 1 0 and AND gate 0 1. So we will see what are the rules for this thing. Okay. So I mean this is pretty obvious. I mean in your case it should be obvious, because you see whenever this is a 0 and a 1, so what our intuition says that will follow. So obviously if this is 1, so this whatever is here will propagate over here. So whatever is the fault list here can be propagated here, as well as the output is 0. So obviously one stuck at 1 at this net is also detectable. So idea is that, so whatever is the fault list at this end can be propagated from here by the deductive fault simulation rule, and also this is 0 1 so here you will get the value 0. So, a stack at 1 fault at the output is also detectable. So, that is intuitively is the case, and that is what is going to happen. So, let us see. So, we have taken another example here. So, this is an inverter and all. So, we put a 0 in the input. So, if it is a 0, so you know that this input is 0. So, this is going to be 1, this is 0, the answer is 0. So, now in the input to the AND gate, this one is 1 0. So, let us study the rule. So, you apply a 0 over here. So, a stack at 1 fault is detected at this net. So, it is this one. Now, the fan out rule. So, this is a 0 and this is a 0. So, obviously, this one gets propagated here and this one also gets propagated here, sorry. And then a stack at 1 fault at this net is here, and a stack at 1 fault at this net is reflected over here. So, this is the case. Now, by the inversion with an inverter, so we know that whatever fault list here will get here. So, we have this one and this one which is propagating from this end. So, these are these two will get propagated over here because of an inverter, and here we had a 0 over here. So, the answer is a 1 over here. So, a stack at 0 1. So, a stack at 0 fault at this net is also detectable. So, this is a new thing that is added, and these two are propagated from the input of the inverter. So, now what is the status? So, the status here is, let us see what is the status. So, the status here was the signal here is a 0. So, this is a 1, this is a this is a 0, this is a 0 and this is a 1. So, now you see what are the fault lists here and what are the fault list here. Then we can discuss. So, now you see, so in this case, so this is a this net is 1 and this net is 0. So, whatever I mean whatever is available here will propagate here. So, this is a very well known fact. Okay, so, I mean what happens is that let us see what happens. So, in this case, so whatever fault that will actually impact this net can be propagated over here because there is a 1 over here. So, that is what we are expecting, and of course, this is a 1 and a 0. So, the answer is 0. So, here is a stack at 1 will be detected at this net. So, this is here. So, we expect that I1 this one will be propagated here. So, this is here, but you see this fault should also have been propagated here, but which is not the case. So, why this fault that is I1 1, why this fault should be propagated? This fault that is stack at 1 at this net, why it should be propagated? Because we failed that in an AND gate what happens. So, this net value is a 1. Okay, so, as this is the continuum, it does not have any, I mean this is 1, then everything from here passes from here to here. So, the whole fault list should propagate, but there is a problem. So, whole fault list will not propagate, as our expectation was that in this case, if it is 0 0, our expectation was that nothing would propagate here, but we saw that only those faults which are common to both of them propagate. Similarly, in this case there is a slight deviation from the intuition. Our intuition says that at this net is 1. So, whatever fault list here will propagate. So, that is why this is propagating, that is true, but you have to observe one thing, that if something this one is common to here and here. So, that common part you cannot propagate. So, let us see why it is not propagatable. So, you can just see why it is not detectable. So, let us study the case. So, in this case it is stack at 0. So, the 0. So, this stack at 1 is detectable over here. So, this is a 0 normal case, fault 1 case. So, 0 1 0 1. So, it is 1 0 because of this inversion, and your output will be 0 slash 0. So, this fault is not detected. This stack at 0 results to a 0 0 here, which is not detectable. Now, why this is not detectable? Because this stack at 1 fault at this net impacts this net by making a 0 to 1, and also this net by making from a 1 to 0. So, what it happens, the output is 0 0, that is normal case also 0, failure case also 0. So, it is not detectable because this stack at 1 fault actually is affecting both. This value is 1 and this value is both this net as well as this net. So, even if this is a 1, this fault, this one should, whatever is in this case should propagate over here, but as this fault actually is affecting both these nets. So, even if this is a 1, these things cannot propagate, but this fault, that is I1 G1 3 1, that is this net stack at 1 is easily propagatable over here, because this is 1, this signal value is 1. So, whatever here is propagates over here, and this fault does not have this impact. So, just this can be very easily verified. So, I mean you apply a 0 over here. So, it is a signal is 1, it is a 0. So, if you just this net is stuck at 1, this net, so the output is 1 in the normal case, and here the signal is, sorry, the signal is 0 over here. So, this is a 1 over here, this is a 0 1. So, the output is 0 1. So, for this stuck at 1 fault at this net, what happens? Normal case it is 0, fault case it is 1. So, the fault is detected at this network. So, that means this net, this is also propagated at this list. Now, why it is possible? Because this stuck at 0 fault, sorry, this stuck at 1 fault at this net has no effect in this line. So, it is this propagates to the output and it can be detectable. But this fault, that is a stuck at 1 fault over here, at this point affects this net as well as this net, both of the net is affected. So, even if this net is 1 and this fault list is available over here, it cannot propagate to the output. So, the rule is fault deduction at 2 input AND gate with N1 equal I1 equal to 1 and I2 equal to 1 is all faults in I2, obviously because this is a 1. So, whatever fault in I2 will propagate, but not in I1. That is, if there is a common fault between this net and this net, so that will not propagate. Even if this is a 1, but any fault which is common to both of them will not propagate, other than whatever fault list here which is not common to between these two will obviously propagate, because this net is a 1 and whenever one input of AND gate is 1, the other gate propagates. And obviously a stacked 1 at the output of this AND gate is detectable, because this is 1 and this is 0. So, the output is a 0. So, any stacked 1 fault at the output will be detected. So, the rule for AND gate with one input stacked, one input as 1 and the other input is 0. So, what is the rule? The rule is, say, whatever one gate is 1, one input of the AND gate is 1. So, whatever you have at the other fault list, other input fault list is obviously directly propagated, because the other input is the 1. But if there is a common fault in between both the inputs of the AND gate, then that fault list will not be propagated, because it is affecting both the lines. So, that is not the case. So, there is same rule, but that is the rule. So, now this is another configuration for the AND gate was left, that is this is 0 and this net is 1. So, here the rule will obviously be the same, just have a look. So, this is the AND gate we are taking, and my normal circuit we are taking. In this case we have now the random pattern is a 1. So, the random pattern is a 1 means it is a 1 over here, it is a 0 over here, it is a 1 over here. So, we can study the rule about 0 1 for the AND gate. So, now as you are applying a 1 over here, so stack at 0 at this net is detected. So, this you are going to have, and in this net by the fan out rule, so this is a 1 1, this is 0. By the fan out rule, this will be propagated over here, as well as a stack at 0 fault at this net will be detected, because this is 1. Similarly, this one will be propagated here, this effect is propagated here by the fan out rule, and this is a 1. So, a stack at 0 fault at this net is detectable over here. So, this is what is the case. Now, because of this inverter, the whole stuff will get propagated over here, and the signal here is a 0. So, a stack at 1 and this fault is detectable by this one. So, these 3 lists we are having. So, finally, what we are having over here? So, finally, we are having, you can see that it is a 1 over here, it is a 1 over here, 1 over here, 0 over here. So, this is the list over here and this is the list over here. Now, intuitively you can say that as this line is a 1, so whatever whole thing here will propagate here. But actually this will not be the case, because this is stuck at 0 and this stuck at 0 is common to both these points. So, this common fault will not be propagated. Other than that, these two will be propagated here, and 0 1 means the answer is a 0 over here. So, a stack at 1 fault at this will be detected. So, this is added. So, we have these two faults propagated. This is the common fault, is not detectable, so is not propagated, and one stack at 1 fault at the output. So, the rule here is again the same. If this fault deduction at the AND gate with in 1 is 0 and into 1 is 1, all fault at in 1, obviously whatever fault here needs to be propagated, because the other input is 1, but not in into. But if there is a common fault over between them, they will not be propagated, and a stack at 1 at the output of the AND gate is also detectable. So, we have seen that how the rules can be determined for all these cases. So, now just let us tabulate this one, the default deduction rule for the logic gates. So, that means what happens is in case of deductive fault simulation is that we apply a random pattern, then we find out the rules, that it is at the input these are the faults which are detectable. Then what we do? Then we find out that what if there is a fan out, or if there is AND gate, if there is OR gate, then we have to apply the rules, and then we have to find out that if these are the set of fault list at the input, then what are the set of fault list at the output, that you have to determine. So, we need rules. So, let us see what are the rules. So, you can see here that AND gate, the 4 cases 0 0 0 1 1 0 1 1. So, these are the outputs, inputs, 4 combinations, these are the outputs. Now, you see, so what it says that if both the inputs are 0. So, we have seen what is the rule if both the inputs are 0, only those faults which are common to both of them will be propagated, and at the stacked 1 fault at the output will be detected. So, we write list of N1 intersection list of L2. That means, whatever is common in input 1 and input 2, that will be detected union O1, that is stack at 1 fault at the output of the AND gate is detectable. Now, you see this case 0 1. So, what we have seen, that is 0 1 means what you have seen. So, some faults actually in this case whatever fault at this list will be propagated, that is in list of all will be propagated, but at the same time you have to assure that any fault at this net will not be propagated. That is, if there is some common fault over here and here, so that is not propagated. So, what we can say is that all the fault list here will be propagated and all the faults list which are here at this point will not be propagated. Then it automatically takes care of the fact that if there is some common thing in between these two, that will not be propagated. Why? Because this input is 1, so whatever here will be propagated, but if there is something common, that will not be propagated, and whatever fault is at the 1 will not be propagated because this input is 0. Basically, this is the idea that this is 0 and this is 1. So, fault list here will be propagated, and as this is a 0 and this is a 1, the fault list here will not be propagated. So, automatically it says that if there is something common in between these two, then that will not be propagated because whatever here is not allowed to be propagated. So, how we write this? We write in a very simple way. We say that L1 all the fault is intersection L2 bar, that whatever here will be propagated, whatever here will not be propagated, and obviously the output is 0. So, a stacked 1 fault will be also propagated or will be also be detectable. This is the propagation list, and this is the output, which is fault at the output of the gate, which is detectable because the output is 0 for the input, this one. Now, for 1 0 you can also see that whatever here will be propagated fault list, whatever here will not be propagated. So, that is L1 in bar and intersection L2, that is whatever here will be propagated, whatever here will not be propagated. So, any fault common in between these two will also not be propagated, plus the stacked 1 at the output is also detectable because the output answer is 0. Now, we have seen the best case was 1 and 1, if both the inputs of the AND gates are 1, then what is the idea? Oh, list over here, list over here, all are detectable, and this is a 1. So, this stacked 0 at the output will be detectable, and whatever list here and whatever list here. So, it is L1 union L2. So, both of them, both the fault list will be propagated. So, this is for the AND gate. For the OR gate, actually for testing purpose or input purpose or whatever purpose, it is just the dual. That is just the dual. If you apply the dual rule, you can find out. So, if it is 0 0, output is 0. So, this is an OR gate. So, if both of them are 0, the output is 0. So, 0. So, we know that in case of an OR gate, if you apply a 0 over here, so whatever impact over here gets propagated because it is the dual of an AND gate. In case of AND gate, if one input is 1, then whatever happens the other outputs get propagated. And in case of OR gate, it is just a dual. So, if the answer is 0 over, both of them are 0. So, whatever here propagates over here. But you know that if in an OR gate, if one input is 1, then the answer is 1 and nothing gets propagated. So, just by applying the dual rules, we will find out that if both of them are 0, then both the list will be propagated, that is the union, and of course, the output is a 0. So, stacked 1 fault will be detected. 0 1. So, here in this case we know that this is very helpful, this will allow you to propagate, but this 1 stops. So, whatever here will be propagated and whatever here will not be propagated. This is an OR gate. So, in this this is an OR gate. So, whatever is the question was, we have a 0 and a 1. So, we know that this whatever here, nothing, this will not be propagated over here because this is a 1 and if this is a 0. So, whatever list over here will be propagated. So, you write L1 bar that nothing of this area will be propagated and whatever here will be propagated, that is intersection L1 into, and as 0 1 the answer is a 1 over at the output. So, a stacked 0 fault at the output will be detected. So, similarly you can find out the rule for 1 0, which is this one, and 1 1 in this case it is just like 0 0 for the AND gate, nothing gets propagated excepting if there is something common fault is for both of them, and 1 1 the answer is a 1. So, in the output case it will be stacked 0 fault will be detected. So, that is what is stated over here in the table. For the NOT gate, we know that whatever is in the input of the NOT gate will be propagated, whatever in the input of the NOT gate it is propagated. So, it is an inverter. So, whatever here is automatically propagated here, but if the input is a 0 over here, we get the answer 1 over here. So, a stacked 0 fault is detected. If it is a 1 over here, the answer is a 0 over here, and a stacked 1 fault is detected. That is what is being stored. And in case of fan out, it is the same thing like an inverter. So, we have seen the fault gate. So, whatever the list here will be propagated here and here. So, whatever is the list they are propagated, and if you get the value of 0, a stacked 1 is detected, and if you get the value 1, a stacked 0 is detected. That is just the reverse. So, if you get the signal value 0, a stacked 1 fault is detected. If the signal value is 1, a stacked 0 fault is. So, this is actually the fault deduction table for the fault list. Now, what happens? So, once you have that, so, given a circuit, you apply a random pattern, then our goal here is that you have to traverse the circuit once, and in the one traversal of the circuit, what you have to do, you have to find out that what are the fault that is detectable. So, here are some rules we are applying, that if there is an inverter, what are the rules, if the AND gate, what are the rules, if there is an OR gate, what are the rules. By just by applying the rule from level 0 to level 1 to level 2, level 3 and so on for the circuit, you go to the output, then easily you can find out the list that all these faults which are in the list are detectable by that input, and then that is in one scan of the circuit this is done. Now, you find out, say there are say 30 faults in the circuit, then in one scan of your circuit you find out that some 20 faults have been detected. Now, if some 20 faults have been detected, so it is a good news. So, another 10 faults are remaining. So, again you have to apply these things and you keep on going. This is a very good and advantageous approach compared to serial and parallel fault simulation, because in one go you can deduce the information about all the faults. But here you have to think once that once I have applied one pattern, then I have gone for a deductive fault simulation at the output, then I find out that these are the faults are simulated, are detectable, then I drop them and then I take a new random pattern and again I redo everything. So, what was our discussion on fault simulation by event driven simulation and compiled code simulation? So, in compiled code simulation, what was the idea? That one pattern you apply, one fault you do find out and then forget everything and then again do another simulation. But we find out that the circuit structure is very simple. The circuit structure is not changing from one fault to another fault as such. No gate is added or no gate is deleted kind of a thing. So, why we are unnecessarily computing the circuit values again and again when you are going for one pattern to another pattern. Then we saw that event driven simulation is a very good approach. In this case, what we do? So, we find out the output or the input under fault or normal case, then we retain some values or say all the values of the circuit we retain, and then what we do when we apply another pattern or another fault maybe, then we should able to recompute only those portions of the circuit which got changed as an impact of something, impact of a new pattern or a new fault or something. So, that is the idea, that is this is missing in our deductive fault simulation. So, in one fault we apply, then we scan through the circuit by applying the rules in the table which you have seen, then we find out these are the list of the faults which are detectable. But we generally cannot or generally do not save anything in that algorithm, and again we have to redo everything. So, the last fault simulation technique we will study today is the concurrent fault simulation. So, that is actually same thing as deductive fault simulation kind, that in one scan of the circuit you are going to find out what are the faults that will be detectable, but at the same time we are not going to throw away the results. So, if by applying one pattern we find out that these faults are detectable, then we do not eliminate all the results. We apply another pattern and then we will try to recompute only those things which are getting changed, that is a event driven simulation. So, you can think that concurrent fault simulation is a event driven simulation plus deductive fault simulation. So, that idea you have to feel. That is what he is saying, that deductive fault simulation which we saw last can determine all the faults detectable by a random pattern, fine, but when a new random pattern is applied, the whole process has to be redone. That is just like a compiled code simulation. So, you have to do something better. So, in the last, that is concurrent fault simulation, a technique similar to deductive fault simulation, but you have to retain the information that what I have done. So, you have to retain when you are going for another random pattern. So, in a concurrent fault simulation, when a random pattern is fed, it needs to compute only that information which got changed. So, that is the idea for a what do you call a event driven simulation. So, concurrent fault simulation get motivated and advantage by event driven simulation over the compiled code simulation. So, that is the basic idea. So, you will see the basic concept of a concurrent fault simulation. So, let us take an AND gate. So, this is your AND gate say, and then you apply 1 1 and the answer is a 1. So, this you have to first draw this normal condition. Then you have to find out that these versions of the gates, we have to draw some versions of this gate which are affected by the different type of faults. Like for example, you see if I0 I1 stuck at 1, that if this net is stuck at 1, then what happens, this input is 0, it becomes stuck at 0, sorry, this is stuck at 0, apply 1 1 you are applying. So, this net is stuck at 0, so this input will be 0, this is 1 and obviously the output will be a 0. So, this is one fault which is affecting this gate. So, this information you have to store somewhere. So, this is the gate which is saying that this net is stuck at 0. So, this answer is 0, this is 1 and the output is a 1. So, this is one version of the circuit with a stuck at 0 fault here. Now, and the stuck at 0 fault can be here. So, this is the case, it is a 1 0 because this net is stuck at 0, the output is obviously 0. So, this is another version of this gate when there is a stuck at 0 fault at this net. Similarly, there can also be a stuck at 0 at this point. So, this version is a 1 1 and the output is 0. So, for each gate you attach some gates in the circuit which is affected by at least some fault. See, each gate is associated with a number of gates affected by some faults in the circuit. So, to each gate you have to attach a bubble. So, this is a one gate say, and you have to attach a bubble. So, this bubble will comprise all other versions of the same gate with different faults in the circuit. So, if there are some 30 faults in the circuit, so your bubble will have some 30 faults which are affecting the circuit. I mean, if you have some 30 faults which affect this gate obviously, so then only you will have that this fault gate list in that bubble. So, in other words, in concurrent fault simulation, what is the first step we are going to approach? To each gate we will attach a bubble. In the bubble there will be some other gates, and these are the gates which are affected by some fault in this circuit, only those versions of the gates will be available. So, for if there are 30 faults in a circuit and 20 of them affect one gate, so the bubble for that gate will have 20 more gates of the version. So, you store that one. So, that is what is the first we have to do. Okay, so let us take the same example and let us see how we can make this, then it will become things more clear. So, we are applying the random pattern 1 1. So, we know that we are now considering this gate. So, what are the faults? So, stuck at 0 fault at this net. So, this is 0. So, this is 0 not 1 0 and the answer is 0. So, this one is reflected over here. Similarly, there can also be a stuck at 0 at this net. So, it is I2 0. So, in this case this will be the value 1. This will be a 0 over here, and this 0 1, the answer is 0. So, another fault list you are having for this gate. Now, we already told that this is 1, this net is a fan out net. So, it is different. So, I2 G1 stuck at 0 is also possible. So, in this case you are going to have this gate. So, this is same, these two, I mean stuck at 0 here, stuck at 0 here, means stuck at 0 fault and stuck at 0 fault over here, same effect. So, these are the two gates with same effect 1 0 and the output is 0, but you have to keep the version because they represent two different faults. Now, this 1 1, so obviously a stuck at 0 at this net, so output O1 stuck at 0 is also affecting 1 1, the answer is 0. So, for this version you have this. So, this AND gate has 4 gates in the bubble corresponding to a stuck at 0 fault here, stuck at 0 fault here, stuck at 0 fault here and stuck at 0 fault here. So, for these 4 stuck at 0 faults you have this thing in the bubble, correct. So, these are the 4 things in the bubble. Okay. So, you can also think that this is a kind of a parallel fault simulation, that you maintain an array, but here the array size is unlimited. We are not going for any kind of a computer architecture oriented algorithm. So, whatever if these some 100 faults affect a gate, so you will have some 100 gates in that bubble. So, here we are not using the architecture kind of a thing. So, now just let us look at it is 1 1. So, 1 1 and in this case is a 1, it is a 0. Now, let us study for this inverter what will be the cases. So, for the inverter you can easily find out that normal case it is a 1 and it is a 0. So, if this net is stuck at 0 over here obviously, so I2 0, so this is I2 0. So, if I2 0 what happens? So, this one will be 0, this is stuck at 0 and this one is 1. So, this is reflected by a stuck at 0 fault here, that is the change for this gate. Similarly, a stuck at 0 fault here will also affect. So, now it will be 0 and the answer here will be a 1. Normal case it was a 1 0, but in the fault case it is a 0 1. So, this one I2 0 stuck at 0 effect is also reflected over here, and of course, is a 1 1, normal case it is a 1 and the answer here is a 0. So, a stuck at 1 fault at this one will also be affecting. So, in this case you see the input is 1, the answer should be 0, but a stuck at 1 fault here will make it a 1. So, 1 1, this effect is also shown over here. So, these are the 3 faults which is going to give you the bubble list of 3. So, this is the first case, this is the first case, sorry just a minute. So, this is your first case, this is your second case and this is your third case. So, this has some 3 faults in the fault list. So, this is how we are making. So, now the thing will all the benefits will start coming when you apply another random pattern, but let us first see what is the case. Now, we have so what we have in the normal case 1 1 1 1 0. So, this is also 1 1 and this is a 0 and the answer here is a 0. Now, for this gate also there will be lot of gates in the bubble which is actually affecting this one. So, now let us see how can we find out which are the fault this thing which is number of faults affecting this one. So, you can see that this one depends on three values, the value here. So, these are the two values, I mean this gate 1 0 is the normal case, and then we have to find out for all, we have to find the bubble list for this gate, that is, so we have to find out the bubble list, that is what are the faults which are actually affecting this gate. So, the normal case is a 1 0, the answer is 0. So, you have to find out for all cases of faults or all versions of this AND gate where at least there is a difference. So, here instead of 1, if it is a 0 you have to put, if that means if it is a 0 over here you have to put that version, if there is a 1 you have to put the version, and if there is a 1 in this case you have to put the version. So, all such cases which changes the input signal value or the output signal value you have to put it. Now, you can study this list. So, you can see here the answer is a 1, correct, but now if this stuck at 1, if this stuck at 1 fault is 0, so this gate output will be a 0. So, here you are going to get a 0 and the answer is 0. So, this one you have to keep. So, how we are deriving this? We are deriving this from here. That is, with any signal change, that this signal change if it is from 1 to 0, then you have to put it. Now, how you know that this will be changing, that this fault, this is the fault I1 stuck at 0, this stuck at 0 will result a 0 at this gate output. This is we can find out from this bubble list. Okay, and then this 0 means the signal is changed. So, this one we have to put it, we can put it. Now, you see there is another one which is also the same thing. So, this one is also change this value from 1 to 0. So, that value also you have to put it over here. So, that is a 1, in this case is not affected, the answer is a 0. So, this is the case which is affected. Now, you can also see that this gate is also affecting the signal. So, this one is also you will be available over here, and this stuck at 0, that is this net stuck at 0 means that is this gate fault is also changing this value. So, you are going to have this here. So, what we are having? So, 1, 2, 3, 4, 1, 2, 3, 4. These 4 gates which actually change the signal from 1 to 0, So, they are all actually included in this bubble. Now, you see obviously, now we are going to check for this input. Okay. So, this input means it is a 0 to 1. So, now you can check that if something changes from 0 to 1, that will be included. So, you can see that these are the 3 gates. This one and this one, I think these are the 3 gates which are actually changing the value of this one, correct. This one is changing from 0 to 1. So, now you can see OG1, okay, sorry. So, this gate we are considering, this is already over. So, now you can think that some signals which are changing the value from 0 to 1 we have to include, then I2 G2. So, you can find out that if this is the gate, so I2 G2, this is I2 G2 0. So, in this case here the answer will be a 1. So, this one you can include it over here, and I2 0 is also the case, but actually I2 0 already we are including over here. That is, if this gate, if I2 0 fault is there, so then this actually this one is included over here. So, already this is taken into picture because this fault I2 stuck at 0, I2 stuck at 0 affects this gate as well as this gate. So, in this case the signal changes are from 1 to 0 and it is from 0 to 1. So, both signal changes are there. So, this gate actually can be brought down from this list as well as from this list. Anyway, so this gate is already added. So, this gate is changing the value 1 here. So, 0 to 1. So, this gate impact we are bringing out over here, and O2 G1, that is this one, this net if you can think of as O2 output to this net stuck at 1. So, this is the picture. So, it also changes the value of this one, that is 0 to 1. So, that one also you have to bring it over here, and in this case you can see that this is already 1, and this fault that is O2, that is I2 G2 stuck at 0, this is I2 G2 stuck at 0. So, this one stuck at 0, that this net stuck at 0 converts this to 1. So, here the signal changes from 0 to 1, 1 1, the answer will be 0. So, you have to write that this gate is saying that 1 1, the output is a 1, that is you have to write in that way. Okay. So, and this one, this stuck at 1 fault, sorry, this is this list already we have discussed. Now, this net stuck at 1, this net stuck at 1 actually converts this from 0 to 1 and 1 1, the output is a 1. So, this net O2 OG2 stuck at 1 is also printed over here, and in the end. So, these are the gates which actually get propagated, this 1, 2, 3, 4, 5, 6. These 6 gates are propagated from the previous gate input to this one. So, this you can also say in concurrent fault simulation also, this is just like some fault these are propagated from the previous level to the next level, but here actually the gates, this gate versions are propagated from the previous level to the next. The same concept is there, there is not much change, but and also one more the pattern is there, which one more thing will be here, like we have seen in deductive fault simulation, that here if your answer is 0, then this stuck at 1 fault this gets detected, that has to be added to the list. So, in this case also the answer is, we are saying that the pattern is 0 1 0 0. So, any signal change will be affected. So, signal change at this net will be O1 stuck at 1, then this signal change will be a 1. So, this gate list is added, that is 1 0, and the here answer is a 1, because this net is stuck at 1, this net is stuck at 1. So, the last signal at the signal change at the output. So, this 5 fault, this gets 1 2 3 4 5 6, these 6 are propagated from the previous values, and this one corresponds to a stuck at 1 fault over here. So, in this case, so this is how we get this fault list concurrently, we generate this one. So, this still now you might see that the concurrent fault simulation is nothing but it is a deductive fault simulation only. In deductive fault simulation, what we are doing, we are just propagating the fault lists from one part to the other part, and here we are actually propagating the bubble list of the gates. Otherwise, there is no difference. The difference will start coming into picture only when we will change this random pattern. But let us see how many faults are detected. So, now this is your bubble list. So, you know that in this case the normal case the answer is a 0. So, wherever the answer is a 1 at the output of the AND gate, you can know that the fault is detected. So, in this case you can find out that there are two faults, that is O2 G1 stuck at 0, that this net stuck at 1, this is stuck at 1 and this net stuck at 1. So, these two faults are detectable because the output of the AND gate is a 1 and in normal case the answer is a 0. But now similarly also you can see that at O2 also some faults can be detected. Now, what are the faults that can be detected? Here the answer is a 1. So, normal case O2 will be a 1, but here this is 0, this is 0, the output is 0, the output is 0. So, all these 4 faults are detected at this net and this one O2 G1, that this fault and output stuck at 1 fault are detected at this net. So, this is same thing like our what do you call this deductive fault simulation, you can find out the fault list. So, here the fault list is not very directly computable, but it can be very easily generated. That is, in case of a deductive fault simulation, what happens, the fault list will tell you that these faults are directly detectable, that you get a list over here, that is O1 some list over there, okay, and from the list you can say that these are the faults which is detected. But in this case we have to just do simple computation that what in which of the gates this output is different. So, in this case this is different, this is different and this is different. So, these 3 faults are detectable at this net and in this case the answer is a 1. So, 1, 2, 3, 4, these 4 faults are detectable over here. So, this is just a very simple extension, or you can call it the same version of your deductive fault simulation. In the concurrent fault simulation, instead of propagating the fault list, you are just propagating the series of gates. That is the one thing. And another thing you should observe, that in case of deductive fault simulation, we have the fault list which tells this is a fault list, say. So, it tells that only fault 1, fault 2, say fault 3 are detectable, but it will not retain any information which is non-detectable. So, here you see we have 1, 2, 3, 4. So, 4 gates are unnecessarily which are hanging over there, but they are not detecting your fault. So, these things are hanging over there. So, they have nothing to do, unnecessarily they are occupying your memory. But we will see in the next slides that because of these things some information is retained. That is, now if we change the value from 0 to 1 or 1 0 whatever, then we need not recompute the whole thing. We will just recompute whatever changes have happened over here. Only those things will be recomputed, and that is like a event driven simulation, something will be saved. But in case of this deductive fault simulation, even with the fact that we have only the set of say 1, 2, only these 3 information will be available because they are being detected. So, these unnecessary things are not there, but whenever there is a change in pattern, you have to redo everything. So, that is a bit trade off. So, you have to think that if you are doing a deductive fault simulation, then at the output you will have information about only these 3 faults, because these 3 faults are detectable by this one, okay, and this information about this unnecessarily 4 gates, because their output is 0 and the normal case it is 0. So, the faults are not detectable, they will not be there. But the trade off is that whenever there will be a change in pattern, then again you have to redo everything. But here, if with the change in pattern, there will be nothing you have to do much, only whatever changes are required, that has to be done. Like that is what is this thing which we have already discussed, not to redo. So, the concurrent So, this is what is the next slide which we are going to see. So, what we have discussed, that now we have to see the benefits, that unnecessarily we were carrying some additional gates. So, unnecessarily what we were doing? So, unnecessarily we were carrying out some gates which could not detect any fault. So, those gates we were carrying with us. But in case of deductive fault simulation, those gates were not being carried. So, now what is the advantage that you have to illustrate? That I think if you just see, so this gate, this gate, this gate, this were unnecessarily being carried out because the output was 0 and this output is also 0. But now we will see that what is the advantage of carrying these gates, okay, because there is a trade off. In case of deductive fault simulation, we will not do this, but still whenever a new pattern is applied, you have to redo everything. Here will be, let us see here in concurrent fault simulation, by carrying these dead gates, if you can see what is the advantage. So, now let us change the input pattern from 1 1 to 0 1. So, there is a change. So, now as you already seen in what you call our deductive event driven simulation, our computation will only be for those cases where there is a change. So, let us see what happens. So, initially it was 1 1 and the answer was a 1. Then in the normal case we have to apply 1 1, the answer was a 1 in this case. Now, there is a change in signal value, this is changing from 1 to 0. So, what we will do? We will recompute only when things are changed. So, recomputation is 1 to 0, okay. Here it is a constant, so the gate output is this one, correct. Now, this gate was corresponding to a stuck at 0 fault over here. So, it was a 0 over here, 1 over here and a 0 over here, correct. So, this and now this new and, so what we are going, but this is the old thing that is retained. So, you can see now your normal gate will become 0, 1 and a 0. So, that is your normal gate. This is your normal gate looking like 0 1 0 because this pattern you have to change. So, this gate you can delete, okay, this gate which we are going to delete. Now, there is so what is the case? So, this gets deleted. Now, there is another gate was I2 stuck at 0. So, this corresponds to the second gate in this list. If you remember, this I2 stuck at 0 was a stuck at 0 over here. So, now a stuck at 0 over here was, so this input was a 0 because this gate is stuck at 0. Now, there is an impact of changes from 1 to 0 and the answer is of course a 0, but and this gate will be retained. Okay, so, why this gate will be retained? Because initially the gate it was a 1 0 and the answer was a 0. Now, so, when the input signal was 1 1 at the input, so what this gate what the gate with the stuck at 0 fault here look like 1 0 and the answer is a 0. Just stuck at 1 fault at this, it was a stuck at 1 fault over here, the answer you are applying a 1 over here, you are applying. Now, you apply a 0 over here. So, this one will be changing from 0, the output there will be no change. So, you need not compute this and you need not compute this. These values were retained same as in the previous case when we were applying a 1 over here, 1 1 over here, and only the small changes are this one. So, there is a signal change because now the gate, normal gate looks as 0 1 0, this is the normal gate, this one, and here with the fault effect the gate is 0 0 0. So, there is a signal difference over here. So, this gate is going to be retained. So, that is again you can see that what we are doing. So, this gate is retained. So, what we are doing over here? So, what we are doing was a very simple thing, we are going for event driven simulation. So, we are just changing whatever signal here required, this is a change here, this is a change here, and in this case after doing this change, you can find out here is that this gate and this gate remains similar. So, you can drop it, but for the second case there is I2 stuck at 0 fault, there is a signal change from here, this does not change, this remains same. So, these things and these things retained from the previous computation, and we they say that there is still a signal difference between this one. So, this gate is retained. So, some computation that the computation at this level and computation at this level are saved. Now, let us take the third gate. The third gate was I2 G1 stuck at 0. So, this line is stuck at 0 over here. So, now the signal you are applying here is a 1, this is a 0 over here. So, in this case this is a 0. So, we know that this stuck at 0 over here, the signal, this signal is 0, this is only a change over here, and this thing is retained and this thing is retained. So, you can find out that for the ordinary gate the signal was 1 0 1 0. So, in this case it is 0 0 and answer is a 0. So, again by the same logic of I2 stuck at 0, this gate is also retained, but this computation and this computation is saved. Now, let us look at the output of the gate, but it is changed. So, whenever the faults are not over here, you are applying the change from 0 1 1 to 0 1, and here is the stuck at 0 fault over here. So, you can say that this is a change from this signal and these signal values retain same from the previous computation, and now this gate is having 1 0, from 1 to 0 you are going here. So, the answer is the same and the answer output is 0 and this is 1. So, these two gates become normal gate and this output stuck at 0 gates become similar. So, this gate also has to be dropped. So, now what happens? These two gates dropped and these two gates keep on retaining, but we need not compute the value here, need not compute this value, need not compute this value, they get just carry propagated from the previous one. Now, in this case you see if you are applying a 1 over here, then this circuit changes over, the signal changes over here. So, the fault list at this gate all the things will be retained, because the signal change is over here and in this line there is no impact, there is no impact in this line. So, if there is no impact in this line, then you need not think about anything, you can just copy paste what was available over here. So, if it is I2 stuck at 0, okay. So, you are applying a 1 over here, so it will become 0 over here, that is 0 over here and the answer will be a 1 over there, but in the correct sense it should be a 1, it should be a 1 and the answer should be a 0. So, that is this fault list, this gate is already retained from the previous list. So, previous list of when the input was a 1 1. So, what we have seen in this example that whenever the fault is affected or this input changes this one, so this thing can directly be retained over here, because the change in this input from here does not affect this one. So, this is the advantage of a concurrent fault simulation over deductive fault simulation, that many of the portions of the circuit, like this portion of the circuit, this portion of this is not affected by this change in this one, and so you can directly add this bubble list. That is, you need not even think of in this case of the AND gate, there is a change over here. So some impact on this gate is happened. So you go on deleting these gates and you keep on retaining, and in these gates also you have saved the computation of this input and computation of this input, but for this portion of the circuit you need not think about anything, just you retain the value. That is what is the importance of a a concurrent fault simulation over a deductive fault simulation, that you need not keep on this thing. Now by the same rule, so this was this is the change. So in this case this will be the change from 1 to 0, and now you can see that this corresponds to this net stuck at 0. So this whole list is from the old computation. This is from the old computation. So this is what we are having from the old computation. So now you can see that because of this change, so you will be normal condition will be 0 0, and the answer is a 0. So this is about this gate. Okay. So now you see that I1 this stuck at 0. This stuck at 0 means it is 0 0 and 0. So this gate exactly becomes similar to the normal case of this one. So you can delete it. Now I2 stuck at 0. So this net is stuck at 0 if you think. So I2 stuck at 0, if you think, so this one will become 0, this one will become 1. So this is a 1, okay, and these two are same as in the previous computation. So this gate is retained. So in fact what we are doing over here, so just by this change from 1 to 0, then this is the old list which was available with us. So we are just finding out what are the changes by this change, what are the changes in these gates we are finding out, that is the bubble list, and if something becomes equal to 0 0 0, that we are deleting, and if something is not becoming equivalent, we just retain it. So for I2 0, there is a signal difference between this one and this one, so this gate is retained. Now I2 G1 stuck at 0, so I2 G1, this one if you consider stuck at 0, so then what happens? This gate, this one will this stuck at 0, so there is no this one is stuck at 0, so this one is a 1, so this answer is a 1, this is stuck at 0, so here it will be a 0, output is 0. So now the thing is that for this case you apply a 1, you get a 0. So this I2 stuck at I2G, this part stuck at 0 will lead to this gate is 0 0 0, which becomes equivalent to the gate under the normal condition whenever you are applying 0 1. So this gate will keep on deleted. Similarly, you can easily find out that if this is a stuck at 0 over here, I2Z1 0, then the input becomes 0 0 0, which is again similar to the normal condition of this gate under 0 1. So this gate is deleted. So this way you find out that 2 of these gates deleted. Okay, so here 2 gates are deleted, this one is retained. Now you just think of the case I2 G2 stuck at 0. So this one is stuck at 0 if you think, then what happens? Then this one will be 0, so this one will be a 1, and here there will be a change from 0 to 1, because initially the pattern applied was a 1 over here. Okay, so the pattern 1 was applied 1 over here, and if there is a stuck at 0 fault here, so there is no effect over here. Okay, so no effect was here, so it was 1 1, the output was a 1. So your gate was looking like 1 1 and the output was a 1. So this was the old computation. Now you are applying this change, so this change is leading to this change is leading to this change. So this gate will be now having 0 1 0, but still this gate will be retained because there is a signal difference over here. So you can see that because of this change in this one, this computation is not affected, only this change and this change you have to get. So some cases these faults are, some computation is saved. So this gate is retained, that this gate I2 G1 this I2 G2 stuck at 0, this I2 G2 stuck at 0, this case is retained over here because there is signal difference, but only you have to compute this change in the input which is arised because of this change. So this is retained. Now similarly you can easily verify that what are the other gates which are retained is O2 G1 stuck at 0, that this one if you are going to get a stuck at 1, then this one will be changed and then output will be changed, this one will be a 1, but there is a signal difference with this normal gate, so this is retained, and OG3, the output G3, so if you just think of this case, so this fault is also going to be retained because this is the stuck at 1, okay, and this is the signal change only because of this signal change. So you write like this, and the gate which corresponds to O1 stuck at 1 is still retained because there is a signal difference, that is in the just because of this change application. So, it will become 0 0 0 in the normal case, but if it is stuck at 1, the answer here will be a 1. So, by the previous computation only you can say that this gate is retained. So, what we have done basically by this signal change, what happened by this thing, this is a signal change which has happened, which is not affecting this gate in any way. So, directly you retain all the gates without doing anything, but for this gate and for this gate there is some changes, this is the signal change that has happened. So, based on that you find that this gate, these gates get deleted, because here the signal after this change it will become 0 0 0 and these gates will also become 0 0 0, which becomes equivalent to this. So, these are dropped, but for this things this one and this one they retain because there is a signal change. So, now you can easily derive that which are the faults which can be detected over this. So, you can find out that there is a signal, this is the fault which is detected, because here is the answer is a 0 and here the answer is a 1. So, one fault is detected, but this one now the answer becomes 0 and this one the answer becomes 0. So, this fault does not get detected by this one, and in this gate you can see that none of the faults get detected because the answer is a 0 over here, the 0 over here. So, in this case also the answer is a 0 over here. So, none of the faults get detected by no additional fault, I mean what you can say by this one, only these faults get detected. So, but what essentially we have done, so we have retained this gate directly without going for any kind of additional computation, and in this case also we have gone for some computation, but the computations are minimal. Here actually we did not do any computation, but still directly we can find out that we can delete it. In this case only these some small computations which are pointed where we have to do, and then we can find out the fault list. So, now after doing this what we have done, we have just said that these are the remaining gates, these are the remaining gates and these are the remaining gates. Now, there is a small thing you have to do. So, what advantage we have got? So, we have just converted. So, what you can call that by concurrent fault simulation, as we are retaining the information about the gates. So, we can just for the new change in input, what we can do is that without doing for any recomputation, we can find out this one, we can find out this one, and we can find out this one with this is without any computation, and here some small computations are required. So, we are reusing the information whenever the pattern is changed, but now some new faults will also get added. For that obviously you have to do the recomputation. So, what is the advantage of concurrent fault simulation? So, whenever a new pattern is applied, so what we are doing, whatever is possible, those informations we are retaining, like this information we are retaining, this information we are retaining, this information we are retaining, but there will be some new faults will also get added. For that you have to complete afresh. So, in concurrent fault, in deductive fault simulation we are remembering nothing, but in concurrent fault simulation we are remembering whatever is possible. Like for example, I tell you what are the new gates that are added. So, now you are applying a 0 and a 1. So, obviously what is the new fault that is going to be added is a stuck at 1 fault over here, that is I1 stuck at 1. So, if it is I1 stuck at 1, then what is the signal value? It will be a 1 over here, it is 0 and the answer is a 0. So, this is one fault which has to be added, this stuck at 1. Previously we were applying 1 1. So, obviously no question of stuck at 1 was here. Now, you are changing the value from 1 1 to 0 1. So, obviously one stuck at 1 fault and this one will be applied. Now, you see, so now this is a new fault. So, now in this case previously you were applying, previously if you remember we were applying 1 1 and the answer was a 1. So, in this case we were detecting a stuck at 0 fault. Now, because you are changing the value from 1 1 to 0 1, so obviously the answer here is a 0. So, obviously one stuck at 1 fault as OG1 will be added over here. So, in this case it is 0 0 0 1, but here instead of 0 the answer is 1. So, 2 more gates have been added and obviously these 2 faults are detected here, and you have to see that these are all recomputed. For here concurrent fault simulation and deductive fault simulation have no difference. You have to again recompute all these things, but where we have saved here, we have saved here and we have saved here. So, whatever is possible we are remembering. Similarly, for this gate if you check, some new gates will be added. So, what is the new gate that is added? So, now obviously you can see that this is was stuck at 1 fault here, this is actually 1, this stuck at 1 fault over here. So, if we stuck at 1 fault, then the answer is a 1 over here. So, there will be a signal change here. So, this gate will be added by this one. So, stuck at 1 here means the answer is a 1 over here. So, instead of 0 the answer will be 1 1 1 0. So, this stuck at 1 fault is a new fault which is added, which is get retained over here. Then actually OG1, so this one was a new gate, this one that is stuck at 1. So, initially it was stuck at 0. So, this new gate is also added over here. So, it is 1 1, the answer is 0, and of course, previously I think previously when you were applying 0 0, so sorry, previously when you were applying 1 1. So, the answer was something whatever. So, now here it was stuck at 0 in the previous case. Now, you have to apply a, because here it is 0 0, the answer is 0. So, a stuck at 1 fault at this net will be applicable over here. So, these are the new gates. This one, because of this stuck at 1 fault, which is newly added over here because of the change in pattern. So, these are the 2 gates which is added, and now in this case the answer is a 0 over here, 0 0, the answer is 0 over here. So, you can add a stuck at 1 fault here, this is O3 stuck at 1, input is 0 0, the answer is 1 because this net is stuck at 1. So, 3 gates get added over here, and so you can say that because of this pattern, so the output here is a 0. So, what fault can be detected? This stuck at 1 fault can be detected over here, and this and these 2 fault, that is a OG stuck at 1, this fault is detected over here, that is OG stuck at 1 and I1 stuck at 1. So, these 3 faults are again detected by the pattern 0 1. So, these new gates are again totally based on recomputation, but still what is the advantage, that what are the remaining gates, this information you can retain from your previous pattern, that is 1 1, and whenever you change the pattern to 1 0. So, computation regarding the remaining gates are very minimal or no computation is required, you just get the values. Only for the new gate you have to do computation. So, concurrent fault simulation over deductive simulation is advantage is that you retain whatever is possible. In deductive fault simulation you retain nothing, but here you try to retain something as much as possible, but still then what is the penalty we are paying, that some of the gates, like for example the dead gates, if you remember. So, these gates had no effect, like this gate, this gate, this gate, actually we are just keeping it, we are just carrying the dead animal, you can think. They were not having any effect, they could not detect any fault in the previous case, also not in the present case, but still we are keeping this information because they may be reused in some other cases. So, that is by carrying these dead animals, you can think that some computation is safe, that is what is the idea. So, here also you may not know that whether this gate would lead to any kind of fault detection, but still we are retaining them because we feel that sometimes it may be possible to do this one. So, that is basically the idea of concurrent simulation. Okay. So, that is what is the case. So, now what was our discussion, you summarize. So, only 3 gates correspond to fault being detected at this one. So, what is the requirement of 7 gates in the affected list? That is the very important thing. That is, if you look at this example. So, in this case that I was saying, so only this gate and this gate has an output difference with this one. Then why are you carrying these dead animals? So, that is the question that is being asked over here, that only 3 gates detect this fault, then why are you carrying all this? The idea here was that whenever there is a change in the random pattern, then those dead gates may help in detecting some other faults which we have seen, and then this recomputation is safe. That is what is the idea of a concurrent fault simulation over a deductive fault simulation. In deductive fault simulation, we do not carry anything. What we do? We do not carry anything, we just for a pattern we find out what are the faults that is detectable in one go. That is why the fault list will have only those elements which are detectable, and then we forget everything, then we apply a new pattern and do it. But in case of your concurrent fault simulation, what we do? We compute some bubbles for all the gates. The bubbles for the gates are having some values. If there is a signal difference with the gate, we keep that faulty gate in the bubble list, and we retain all the gates at all the levels, even if it detects a fault, even if it does not detect a fault. Now, whatever faults are detected, we are very happy, we can drop them, but these dead gates, that is they are having some signal difference with some gates, but they are not able to detect a fault, still we are retaining them when you are giving another input, another random pattern. Then that new random pattern, that is dead gates may help to detect some faults, then those recomputations are safe. So, that is what by saving some recomputation, but still we have to carry the dead load of some gates in the memory. So, that is the advantage and disadvantage. So, that was about the fault simulation. So, to conclude, we can say that concurrent fault simulation helps in random test pattern generation. We apply some random patterns and then we find out what are the faults which can be detected by them. So, you can use serial, which is the slowest one. You can have parallelism. If your computer supports lot of parallelism, then you can go for parallel fault simulation. Otherwise, you can go for deductive fault simulation or concurrent fault simulation. If you are using deductive fault simulation, in one go you will find out what are the faults detected by a pattern, but you do not remember anything. Next pattern you apply, you have to redo everything. But in concurrent fault simulation, you retain some information that can be reused, but for that you have to sometimes carry the dead load of gates which have not helped in any kind of fault detection for the current pattern, but for the next pattern they may do some help, so you have to retain them. But now we see that experimentally it has been seen that this procedure of random pattern based fault generation or whatever can help only for going about 90% of the faults. Remaining 10% of the faults are very hard to detect faults, and that you have to do by what? You have to go by random sensitized, propagate and justify approach. So, in the next lecture what we are going to see? We are going to see that if somebody or some algorithm can tell you that these 90% of the faults are easy to test faults. So, apply random patterns for them. These 10% of the faults are difficult. So, do not try for them. So, that will be very good. So, at least in the fault simulation we will not touch the 10 difficult faults. We will only touch the 90 easy faults to do that. But here if nobody tells you that which is the easy fault, which is the difficult fault, then you are in a blind case. Even for these 10 difficult to test faults, you are applying the random test pattern generation based algorithm and you are failing every time. For all the random patterns you are not able to generate a test pattern for this. So, next class we will see some kind of example of algorithms like swap algorithm they call it, which will tell you which are easy faults and which are difficult for tentatively. Then you apply random pattern for the easy faults and you keep aside the difficult faults for sensitize, propagate and justify. Now, before we conclude, let us come to the question and answer session. So, we are saying that what is the main advantage of compiled code simulation versus event driven simulation. So, here what is the answer? So, we have already discussed many times right now for the concurrent fault simulation, deductive fault simulation and for normal fault simulation and normal circuit simulation kind. So, in compiled code simulation, we have convert the circuit into a program and you execute for a pattern. Then you forget everything. You just change anything, then again you have to redo everything. But in what you call event driven simulation, we remember whatever was we have done in the previous iteration, and only those changes for a fault or for a pattern, whatever are the small changes in some regions of the circuit, only there we do the recomputation. So, what is the advantage, disadvantage? Obviously, event driven simulation is faster because you do not recompute anything which is redundant, but at the same time you have to remember the values from the previous iteration. So, you have to have some extra thing in the memory, but gain is speed because we are avoiding recomputation. Second question is, among all the 4 fault simulation algorithm which you have seen like serial, parallel, deductive and concurrent, which depends mainly on the computer architecture. So, among them we have seen only the parallel fault simulation is dependent on architecture because to each net you assign an array and the length of the array is processed parallelly. So, you have to think about bit parallelism. So, if your computer has 32-bit parallelism, so you can have maximum 32-bit array in all the inputs. And for all other cases like serial, deductive and concurrent, we do not at all think about the memory of the computer, we do not think about the parallelism of the computer, we rather think that what are the fault list size, what are the affected gate list size, and accordingly we attach to each gate or attach to the fault list. So, that depends nothing on the parallelism of the computer, it is just a program, and we think that what is the case? We compute that for this fault gate list, these are the fault gates we have to add, that is fault version you have to add. For these gates, this is the fault list you have to add, just we keep it. We do not think what is the architecture, what is the parallelism of the computer available and that many fault lists we have to add, nothing like that. So, a gate, this gate has so many gates in the fault list, just keep them. But in case of parallel fault simulation, only those number of patterns or those number of bits can be operated on, that much parallelism is supported by your computer. So, that is why among all the 4 fault simulation algorithms, parallel fault simulation is mainly dependent on the architecture. The last question is, when the procedure for test pattern generation by random, this one is stopped and ATPG algorithm by propagation sensitization is taken. That is, we start applying a random test patterns and find out that 10 faults are detected, next random pattern 9 faults are detected, we keep on going for it, and after some time we have to stop. That what is the stopping criteria? The stopping criteria is when you find out that I am applying some random patterns, the number of new faults which are detecting is very less or sometimes even 0. Then you apply a random pattern, number of faults detected initially will be set 10, next random pattern 12 and then random pattern 8, you keep on doing it, but after some time you will find that the number of random patterns you are applying, the number of new faults detecting is 0 or very less. So, at that time you can say that I have to stop because the adding of random pattern is not helping me in any way and I have to go for sensitize, propagate and justify approach. So, thank you, and we come to end of the lecture on fault simulation. In the 3 hours lecture was on that, and next class we will see that can somehow how we can find out which are the difficult to test faults and which are the easy to test faults. So, difficult to test faults we will go for sensitize, propagate and justify approach, and easy faults we will go for random pattern based generation. So, with this we come to the end. Thank you.